Hello, I'm Joseph Huber. I work at AMD, and I'm just going to be talking about some of the weird work I've done trying to get like a standard C and C++ toolchain that runs directly on the GPU. So, GPUs have come a long way since the humble beginnings of fixed function graphics hardware. Now they do like a lot of general purpose or GPGPU stuff, they say. But even with that being said, you look at a lot of the GPUs and they kind of lack the same tool chains that even the simplest embedded processors have. So I was like, if these things are really general purpose, can I just run arbitrary C and C++ on them? And that was the, I guess, motivations behind doing this, even though some of the stuff isn't practical. But it's more about the journey than the destination, I would say. But even with that being said, it allows you to trivially port things to the GPU, and you get generic implementations of a lot of fun things like math, thanks to the LLVM Libc team. So if we're talking about porting existing C and C++ libraries to the GPU, that kind of begs the question of how do you do that, right? Because there's lots of options in this space. So I'm sure many of you are familiar with CUDA or its doppelganger HIP. So this is pretty ubiquitous for targeting code on GPUs, right? But when you actually look at what we're trying to do here, we're just trying to compile some code that runs directly on the device. And CUDA is what we call like an offloading language, which means it combines heterogeneous compilation jobs of like host compiles and device compiles for even multiple architectures into one like mega Clang job. And that introduces a lot of build system complexity that I'm sure anyone who's like tried to do CUDA through CMake can tell you about. So also what's kind of annoying about it for this is that you need to manually put stuff like global and device on each function. But with that being said, let's kind of like take a look at how stuff like CUDA is implemented and maybe we'll learn something, okay? So we have this simple AXPy example that exists in every GPU related slide deck as far as I can tell. So you have this decorator on the function and then you have some weird calls to these block index things and you basically just have C++ code, right? So you then compile that with these like magic Clang options, and if you look at what the compiler is actually doing, it's passing that code to the Clang front end with some magic language options set. And then if you look at what the runtime's doing, it's basically lowering those block index calls to these built-in functions that Clang supports. So you can see this is peeling back the layers of what's going on here. But we don't want to use CUDA for now, so let's look at some other options we have. So the next one is OpenMP. This one is more of a standard C++-ish flavor solution, and it basically does everything with pragmas. So it's got the same issues that I have with CUDA, which is related to build systems mostly, and also needing to like manually decorate things with saying what's on the host, what's on the GPU, because since it's heterogeneous, it doesn't want to assume that everything is shared. So let's just look at this again. We have the same AXPy example, and we're doing this pragma, which basically turns this loop into some collection of runtime calls. And then we compile that, except doing C++ with the -f OpenMP flag set, and we basically get a Clang front-end job with the AMD triple set with some language options for OpenMP. And then if we look at OpenMP's runtime, you might see that it looks a little similar, right? We've got the exact same Clang built-ins to do the magic GPU stuff. So finally, I'm going to think about OpenCL, because OpenCL uses a much more traditional compilation approach, which solves a lot of the issues I have with the offloading languages for stuff like this. But the problem I have with OpenCL is that it is intentionally limited in the types of features it provides to try to make it run on as much hardware as possible. Whereas I'm more interested in exploiting the high-end hardware that most people have access to these days. But, and in that is stuff like, function pointers or recursion. These things are, I think, explicitly forbidden by the OpenCL standard, but exist in a lot of existing programs. So there's no real way to port that. But either way, you can look at this, and you've got some decorator on your function, you've got some runtime call, and it basically looks like C or C++. You run it through the compiler, and I'm assuming you get where I'm going with this. But you take all of that, and I'm like, well, what's the easiest way to port an application? And I think the answer to that is not porting it at all. So you've seen that pretty much every single one of these offloading languages is just kind of some front end into Clang. So why can't we just use C and C++ directly, right? And it turns out that Clang already has an option to directly target different architectures. It's called -- target. So if we're targeting our, amazing, great AMD GPU, of course, we just do -- target equals AMD GCN, AMD HSA, and we invoke that same Clang target you saw in the previous slides. So if we do that, we can just take some like ISO C++, this is like standards committee approved C++, and because, all things like CUDA could handle this, and they're just based off of C++, we could easily just pass this through Clang and get functional device code that does this matrix multiply in this very CS 101 way. Now, obviously, the problem with this is that it's very slow because you're going to be running this on a single thread, and obviously you do not want to run your $1,000 piece of hardware as if it were a $10 Raspberry Pi. So if you want to really use C++ on the GPU, you kind of need to break the conditioning of the standards committee and go into the wonderful world of compiler extensions. So you'll see here that this looks a lot different. It's not super important what the code does. It's just like a blocked matrix multiply that any introduction to GPU programming would give you. But what's important here is that you see we have like special decorators on the function that make it use the calling convention for kernels. And then we have these address space things, which are just target specific attributes for which type of memory this resides in. This is pretty much one-to-one correlation with CUDA's shared keyword. And then we have these like built-ins, the same ones you saw from the runtimes before, that get you things like the grid ID or the thread ID. And then we also have in the loop, we just have these barrier built-ins that are the same as sync threads. Now, you might look at this and think, well, that looks terrible. I don't want to do that. But first off, I have an RFC that tries to provide a resource directory header that will at least give you normal names for these things. It's more similar to what OpenCL has. And second, I think it's more important about how if we shift our perspective on how these GPU languages are compiled, we can do a lot of fun things with it. Because I'm sure, as many of you are aware, this is just cross-compiling. And people have been doing cross-compiling for quite a while now. So pretty much there's lots and lots of support, even in Clang and LLVM, for these types of things, right? We already have build system support for it. So when you start thinking about it like that, any cross-compiling thing is basically targeting a toolchain. And if you start thinking of the GPU as a toolchain, well, any complete compiler toolchain has, a compiler front end. We've already got that. It's Clang. It's an assembler. We have that. It's called like what LLVM machine code.
Clang is an assembler.
Oh, yes, it's also an assembler, but it includes. We also have a linker, ld.lld basically. But we don't have any runtime libraries, really. Like, we do have some runtime libraries, but not really. So, with that in mind, let's just port the existing LLVM C and C++ runtimes to the GPU. And how do you want to do that? Well, as I mentioned before, LLVM already has tons of support for cross-compiling. So I'm sure many of you are familiar with like the runtimes build of LLVM that a lot of the projects like Libc++ that was just talked about use. Now, what's really interesting about this build system is that, one, it basically lets you use a just-built Clang, which is really important for the GPU, because if you recall from those previous slides, all of those compiler extensions said Clang on them and not GNU. So you pretty much need to use Clang for any of this to work. And what's also really interesting is that you can compile the runtime for multiple targets. So if you use the LLVM runtime targets CMake option, you can pretty much enable all of the triples that you want to target for this. And then once you have those enabled, you can then individually pass arguments to each individual toolchain, right? And this syntax here of like d runtimes _triple _var, it's kind of ugly, but it's very powerful once you get used to it. So what it allows you to do is like, we have this runtimes build here, where you have like your x86, which is like your default target for your standard 64 Linux. And then we could enable like, I don't know, the OpenMP or the offload targets if we want to do OpenMP offloading. And then for the AMD target, we could enable the Libc, compiler RT, Libc++, all this stuff. And then for like maybe the NVPX target, we just want Libc. You can do all of that individually because you have the control for each target as its own individual target. Okay. So, and because that already exists in LLVM, we get to exploit the exact same handling that other toolchains get to use for doing this, which is handling through multilibs. So each runtime target basically gets its own directory. If you set this LLVM enable per target runtime dir thing, that's default on in Linux. I think it's off on Windows, I don't know. But what it allows you to do is get a directory structure that looks something like what's on the right here, which is you have each relevant thing, like the include directory and the library directory, is qualified with the target's triple. And because it is qualified, that allows you to name all of the libraries the same things, like libc.a or libm.a, or have all the standard C headers, and they won't conflict with your host build that you probably care about using. And what's also interesting there is that because it will include all of these for you when you do --target equals AMD or whatever, all you need to do is pass like -lm or -lc, and it'll just find those libraries for you as long as it's in your toolchain. So that's pretty much the plan of how this will look out. So let's actually just pass those runtimes to the runtimes build and see how that works. So first was LLVM Libc. I actually did talk about this last year. If you really want the details, you can go back and watch that on YouTube. But pretty much the C library is the basis of all of the other interesting applications, so I figured it was a good place to start. And what's really neat about the LLVM C library is, as you saw, it was highly configurable. So you can kind of just enable this subset of functions that actually work on the GPU and then add more as you go. So system calls, as I mentioned last year, are handled through these remote procedure calls. Long story short, it's a client-server protocol where you just have a CPU thread and a GPU thread basically communicating through some mutual exclusion. Okay, so on the right here, I just have something I copied from the entry points list, and I just put that there to show that, NVIDIA only has one printf. I have every printf. So it's a motivating example. So what's really cool about this as well is that if we're talking about treating the GPU as a regular toolchain, you'll notice that if you've ever done any work with like a normal libc build, they will have like a startup object, and that handles your things like starting up your main application and your start function, right? So we could emit the same thing for the GPU, and that allows us to start thinking of like just calling a main function on the GPU. Obviously, you wouldn't want to do that if you're writing something that's supposed to run fast, but that's really helpful for unit testing because it allows you to just copy-paste existing unit tests and run them directly on the GPU. And in order to actually run that, many people who do cross-compiling are already familiar with the concept of emulators. So you just put some program in front of your executable, and then it'll run it for you, and you basically test it on that target. Now, I don't have an emulator, but what I can do is write a similar tool that just launches it on the GPU for you. And that's just something I call like a loader. So once I have that built, I can also just do the same treatment to the compiler RT directory, because Clang wants to be able to emit built-ins in some cases, like not all cases, but some cases, so it's nice to have. And porting this was pretty much straightforward because it's just C, and as I told you, it's just cross-compiling. Compiler RT already has support for cross-compiling to like a million different targets, so the GPU really wasn't that special once I stripped away all the weird offloading stuff. So all I had to do was just add a few cases for like setting like one or two flags, and then it just worked. And now I just have a static library for compiler RT, for libc, and all this stuff. And it pretty much lets you do weird things like I have here, which calls a main function, just does fprintf to like stood out, and then prints some random like argv value. And you can see I compile this, target it as, same as you would with cross-compiling, do -flto to get amazing LTO stuff. You need to do -mcpu, or else there's like node backwards compatibility on GPUs, so you need to specify that. And then you do link in all the nice libraries we've made, and Clang will automatically handle finding those for you, and then just run it with a loader I wrote, and now you just have something that pretends like it's a normal hosted target. So obviously, libc++ is built on top of libc. So once we've got a mostly functional libc, we can just build libc++ on top of this. Now, some of the libc people already did some work to build libc++ on top of libc in LLVM, so thanks for that. And I could just use the same thing and target it for the GPU. And because these compilation jobs pretty much look like the same as every other embedded toolchain wants to do, I pretty much didn't need to change anything at all. All I used was the existing configuration files that libc++ has, and I just put them in a big cache file. The only things I had to change were like maybe 3 or 4 places where I put an if-def to do something different. But beyond that, porting the vast majority of libc++ was pretty much automatic. I turned off things like threads and file systems and stuff like that because I don't really have an idea for how to support it. I could do file system, but I wanted to keep it simple relatively for now. Now, also a brief mention, there are some other approaches that do libc++ on the GPU, but those are mostly approaches that kind of write the stuff custom and then give it a special namespace, so this is kind of in a different domain. And that allows you to do really silly things like this. So you have int main, and this is a completely arbitrary example, but it's just the best I could think of to show that you wouldn't think this code would be running on a GPU, but you can do it. So, we have like a random number generator that's initialized on the work, the thread ID, and then we just initialize a vector with that, and then use std_cout, and this all works just fine on the GPU. Like, does it take forever to link? Yes. Does it use all of your resources? Yes. Is it really slow? Yeah, but it's interesting. So that's all I care about, right? So, and you can see how we compile this is that we just pass in like every single library I just talked about building. We have like the C library, math library, C++, the libc++ ABI, that's also included in there, and the built-ins. Then we just need to tell it to use the libc++ library and also turn off exceptions because I don't know how to do that yet. Maybe I'll do that, but that's even crazier than what I do now, so I'll just leave that for a later date. But even without that artificial example, what's really fun about this is that it allows me to run a lot of the libc++ test suite on the GPU, because it already has support for these custom test executors, because like I said, a lot of people want to run this on embedded systems. Embedded systems tend to use emulators for testing. So I just stuck that with my AMD loader, and I got to run most of the test suite. Now you see there's still a good number of failures, like 154. There actually were that I fixed a lot, thanks to like Matt Arsenault for fixing a lot of these. But it's a good start. I know generally where the vast majority of these are coming from. It's from like weird libcall handlings, but we'll get to it. Okay, so you'll notice that everything I've mentioned was kind of silly. So I just like to bring it back to applying this stuff to the languages that typical users actually care about. So offloading languages, like I mentioned at the start, are very convenient for typical users. And we can still bring what we built here to applications like CUDA or OpenMP or whatever, because all we're doing here is building a static library. And because we have a static library and our offloading target has a linker that handles static libraries, as I mentioned in the first slides, all we need to do is pass these libraries to the device linker phase. And you can do that with this -x offload linker thing. You do need some support that's not default in CUDA. I think I'll probably finally make it default in Clang 20, so look forward to that, I guess. But this allows you to just write stuff in straight C and C++ and then link it in to offloading programs, and it just works. So I really like this way of programming because it's very, it's close to what I'm used to, and then if I want to go back to an offloading language, it's trivial just to put it in there because I can just use regular CMake. So. And you'll see here the example I did here to exemplify this is calling std_cout from an OpenMP target region. Now I had to do this omp declare for the actual global, but I'm working on how to do that automatically. I was having some talks with the libc++ people. Okay, so let's bring that all together, and what have I really accomplished? Mostly just building a functional C and C++ toolchain that targets the GPU. So it's not super practical for a lot of things, but there are things in there that some people might care about. Like, I don't know, I've heard some talkings about wanting std_md span or std_span on the GPU. You can do that with this just fine. That works. And you can also do testing on this. So if you've ever wanted to write int main and run it on a GPU, you can do that. And this is pretty much just a bunch of compiler CMake magic that you don't need to, like, I guess you can look at the slides if you want to build it, but this should be all that's required to do it. I don't know if anyone who like manages distributions is in here. Maybe someday I'll be able to convince them to do this in their tool chain, as long as they support the per runtime target stuff. So then I don't need to tell people to build it. They'll just use it from their distributions packages. So I could probably stay on this slide for ages, but I'll try to keep it more brief. There's lots of questions about like if you actually try to make this more practical, right? So how do you handle things like mutex and threads? Because GPUs have very limited forward progress guarantees, and their way of doing multi-threading is completely different from what like pthreads expects. So if you wanted thread, you need to like have your kernel launch start with some pool of workers that are there, and then you need to have the one thread signal to the other workers to pick up some work, and then you wouldn't have like SymT at all. So I didn't really go there. Mutex, I think you could get to work if you had stuff like cooperative launches, which is like the thing that CUDA and HIP can do now to basically guarantee that your kernel won't be evicted. But really, one of the main issues here are compile times. So the compile times kind of get really bad when you start doing this stuff because libc++ is huge. Like doing std out generated 300,000 lines of LLVM IR. And that takes a long time to run through the GPU backends because they're really, they don't expect you to do things like this. You know, GPU people expect you want to have a highly optimized kernel because you actually want to use your hardware to do what was intended to do. So they do a lot of like quadratic optimizations and stuff. There's ways that we could try to address that, but it's just a limitation right now. For doing HIP and CUDA stuff, as I mentioned before, you pretty much need to declare which libc++ functions are available. Right now, that pretty much pans out saying they're all available, but that's just going to be some header magic that I haven't committed yet. And then there's also issues when you go to these offloading languages because, like, you need to start thinking about what happens when you copy things to and from the GPU to the CPU, right? So if I copy a std vector and then realloc gets called on the GPU, it's going to try to call free or realloc or whatever. Oh, time is up. Oh, sorry, that's questions. I thought that was that. Anyway, I forgot to do this. This was a demo I did, which is compiling Doom for this. So I'll just leave that running while you ask questions.
Thank you so much, Joseph. And as usual, there is one mic on this end. And let me know if you have questions here. Or you can just enjoy the Doom. So.
He'll probably finish playing for too long, but yeah.
Hi. Way to bury the lead with Doom. Yeah. I did want to kind of ask, like, immediately when I saw int main on a GPU, my thought went to, hey, if I wrote a loop and there's like this thing like auto vectorization, like, would it be possible to actually get that to, like, I don't know, make kernels or whatever? Could you actually just write regular C++ and get it to do GPU-y things?
That's kind of, like, as far as I know, that's kind of how GCC tried to do it, where they went away from the SymT model we use in LLVM, but I think you'd need to, like, turn that off, and I don't think we support that. I need to consult with people who do more back-end stuff, but maybe you need to think of it more as, like, vector intrinsics, but it would be funny.
Is it possible? Is it a way to create vendor-agnostic C++ source in this approach?
Yes, so that's what I mentioned briefly in the beginning, is that I have an RFC up on LLVM Discourse that I just have that just does like if-def AMD GPU. It uses the AMD built-in, else it uses like the NVIDIA built-in. Most of these GPUs do the same thing for like 99% of what people care about. You can just provide wrappers for that.
So I assume you're compiling all these libraries to LLVM IR, right?
Mm-hmm.
Have you given any thoughts on trying to compile it to a native image and then having some sort of dynamic linking or something? Do you know anybody supporting it?
You can compile it to native IR just fine, at least on NVIDIA. On AMD, I mean, so on AMD we have some issues with doing the metadata analysis for like the packet launch for how many registers you need. We don't handle that correctly. But hey, if you use all the registers, then it doesn't matter. But you could do that. The main reason we use LTO here is because you can like retarget it, kind of like SPIR-V. But there's like a few caveats that I don't have enough time to go into. So, yeah.
You have more questions? If not, then let's thank Joseph again.